Please pause the video and try this problem. Now let's discuss the solution together. First, we have to choose a problem-solving framework. We notice that this problem mentions the concept of mass and the concept of acceleration and the concept of friction. Friction is a force. Well, all of these concepts could be substituted into the Newton's second law equations. So it looks like we're going to be using the Newton's second law problem-solving framework. We already have a sketch that was provided in the problem, so let's write down what the question is asking us for, representing it with a symbol. So the question is asking for the coefficient of kinetic friction. Try to write down the exact right symbol. So we know that the symbol for a coefficient of kinetic friction is the symbol mu with the subscript lowercase k. Remember, don't say that they're asking us for lowercase f. Lowercase f is the force of friction, but this problem is asking for the coefficient of friction. So it's good to write down what the question is asking you for with a question mark, an equal sign, and when possible, the exact right symbol. Now we show the object's direction of motion by adding the velocity vector to our sketch. The problem says that the mass is sliding down the ramp. So we can see that the direction of motion is parallel to and down the ramp. Here's the velocity vector. Remember that the direction of the velocity indicates the object's direction of motion. Our next step is to check that the given units are SI units. Kilograms are SI units for mass, meters per second squared are SI units for acceleration. So we made that check. This step is not relevant because we're working on a numeric problem. In the free body diagram phase, we want to identify the object that we're going to apply Newton's second law to. Well, the problem mentions the mass of this box. So it looks like we're going to apply Newton's second law to the box during the interval of time during which the box is sliding down the ramp with this a sub x of plus 3.0 meters per second squared. So we identified the object and the interval of time during which we were going to apply Newton's second law. Now we start our free body diagram for that box by drawing the vector for the object's weight. Here we've begun our free body diagram showing all the forces exerted on the box. This dot represents the box. Here's the downward arrow for the weight force. The rule is that the direction of the weight force should be straight down. How do we find the other forces on the box? Well, we move on to the next step and we ask, what are the things that are touching the object? So looking at the problem, we can see that the box is sliding down a ramp. So the ramp is touching the object, as we can see confirmed in this sketch. Now the ramp is the kind of thing that we will treat as a surface, so the ramp is the kind of thing that will exert a normal force. So we need to draw the normal force in our free body diagram. The rule is that the normal force should point perpendicular to and away from the surface. Perpendicular to and away from the surface is this direction. So let's add that direction for the normal force to our free body diagram. Here's the normal force in our free body diagram, pointing perpendicular to and away from the surface of the ramp. Now, remember that anytime you identify a normal force, you need to automatically check whether there's also a frictional force from that same surface. And we can see that in this problem, there is indeed friction. So now we should add the frictional force to our free body diagram. We have to start by asking what type of friction we're going to apply on this problem, static friction or kinetic friction. Well, it's clear that in this case, the object is moving down the ramp, and in this problem that means that the object is sliding down the ramp. So we know that this object is sliding, and because we know that the object is sliding, we know that we should apply kinetic friction rather than static friction. If we take a look at page 2 of our friction handout, different types of problems about friction, we can see that this problem looks like it's going to be this first type. It looks like we're working on a problem that involves an object that we know is sliding. So we expect to use the Newton's second law framework and apply kinetic friction in this case. In our free body diagram, we have to show the direction of the kinetic friction. For that, we should use this rule. Here's the rule for the direction of the kinetic friction force. The kinetic friction should point parallel to the surface and opposite to the direction of sliding. So in this case, the kinetic friction should be parallel to this ramp. We're sliding down the ramp, so the direction of the kinetic friction should be up the ramp. So let's add that to the free body diagram. Here we've added the direction of the kinetic friction pointing up the ramp. Remember that every vector arrow you write down has to be labeled. So here's a good label for this vector arrow. Remember that the symbol for kinetic friction is a lowercase f, not a capital F. And then for kinetic friction, we should use the subscript lowercase k. We used this rule to figure out the direction of the kinetic friction force. The basic idea is friction opposes sliding. The object is sliding down the ramp, so friction opposes that by pointing up the ramp. How can we tell if there's any other forces on the box? Well, we have to ask, is there anything else that is touching the box besides the ramp? And I think the answer is no. In this problem, there's nothing touching the box besides the ramp, so there are no other forces on this box. We've completed this step. Notice that we had to use the idea that every time we notice a normal force from a surface, we need to automatically check if there's also a frictional force from that same surface. And we used the idea that the direction of the frictional force is the direction that opposes sliding. Now we work on our force table. Now, normally we would want to choose and write down our axes. But on this problem, did you notice we were given axes? So in this case, we should simply notice that we've been given this x and y axis that we need to use. That was given to us. That was given to us in the sketch that we were provided in the problem. So we begin our force table. Here's the outline of our empty force table. Let's begin by working on the weight. Were we given a value for the magnitude of the weight? No. Is there a special formula for the magnitude of the weight? Yes, there is. The special formula is W equals mg. So for the mass, we're going to plug in 2 kilograms. For little g, we're going to plug in 9.8. We calculate 2 times 9.8. That tells us that the weight is 19.6 newtons. We put that into our force table. Now we have to break the weight into components. The weight force is neither parallel nor anti-parallel to either of our axes, so we have to draw a right triangle and use SOHCAHTOA to break the weight force into components, and we should do that in a separate sketch, separate from our main free body diagram. Here's the beginning of that sketch. I've copied our number for the magnitude of the weight, 19.6 newtons. That will represent the length of the hypotenuse. Now we'll use this rule to draw the legs of the right triangle parallel to the axes. I drew this leg parallel to the x-axis, and I drew this leg parallel to the y-axis using this rule. Now we'll use this rule to draw the directions of the components. Where we have the head of the overall vector, that will overlap with the head of this component. And where we have the tail of the overall vector, that will overlap with the tail of this component. That makes this the head of this component. So we applied this rule to write down the directions of the components. Make sure that you label both those components. This side was parallel to the x-axis, so it represents w sub x. This side was anti-parallel to the y-axis, so it represents w sub y. Before we work on the magnitudes of the components, we should figure out the signs. W sub x is pointing down the ramp, which is our positive x direction. So we'll make a note that wx will be positive. W sub y is pointing into the ramp, which is our negative y direction. So we'll make a note that wy will be negative. Now we have to use geometry to figure out the angles inside this right triangle. We can start by extending this vertical line down and extending the horizontal line across to make a large right triangle. Now we examine this large right triangle that I've outlined in color. The acute angles in the large right triangle are alpha and theta. That tells us that alpha is 90 minus 30, so we can say alpha is 60 degrees. Now we examine this smaller right triangle that I've outlined in color. The acute angles in this new smaller right triangle are alpha and beta. That tells us that beta is 90 minus 60 degrees, so beta is 30 degrees. So we applied this rule. The acute angles in a right triangle add up to 90 degrees. Now we're ready to apply SOHCAHTOA. The hypotenuse is this side because this side is opposite to the 90-degree angle. Now we have to decide whether we're going to focus on the 30-degree or the 60-degree angle in our right triangle. The conventional approach is to focus on this 30-degree angle because it matches the 30-degree angle theta that we were given. Let's write an asterisk to show that we're focusing on that 30-degree angle. The asterisk shows that we're focusing on that 30-degree angle. Now we can say that this side is adjacent because it's adjacent to the 30-degree angle that we're focusing on. And we can say that this leg is opposite because it's opposite to the 30-degree angle that we're focusing on. Now we're ready to write our SOHCAHTOA equations. Here's our SOHCAHTOA equations. For the length of the opposite side, we're plugging in the magnitude of w sub x. For the length of the adjacent side, we're plugging in the magnitude of w sub y. And for the length of the hypotenuse, we're plugging in 19.6 newtons. Now we can solve these equations by multiplying both sides by 19.6. So we can cancel the denominators. And now we're ready to write the magnitude of w sub x and the magnitude of w sub y. 19.6 times sine 30 degrees and 19.6 times cosine 30 degrees. Doing these calculations, so for w sub x we got 9.8 newtons. And for w sub y, since this digit is a 7, I'll round up this digit, and since this digit is a 9, I'll round up this digit. So we end up with 17.0 newtons for the magnitude of w sub y, and 9.8 newtons for the magnitude of w sub x. These absolute value signs remind us that the SOHCAHTOA equations only tell us the magnitudes of the components. Now it's our job to write down the complete components, including plus or minus signs, in a separate step. Well, we already determined that w sub x should be positive on this problem. And we already determined that w sub y should be negative. W sub y is negative on this problem. This negative sign is crucial. If you leave out the negative sign, you will get the problem wrong. Well, remember that if you force yourself to put a plus sign in front of positive components, you're more likely to remember the crucial negative sign in front of negative components. Also, if you use these absolute value symbols in your SOHCAHTOA equations, that will help you to remember that it's your job to figure out the plus or minus signs in a separate step. Now we're ready to put this data into our force table. W sub x is plus 9.8 newtons. W sub x is plus 9.8 newtons. And our W sub y was negative 17.0 newtons. W sub y, negative 17.0 newtons. We've completed our work for the weight in the force table. Now we have to work on the normal force in the force table. Were we given a value for the magnitude of the normal force in the problem? No. Is there a special formula for the magnitude of the normal force? No, there is not. Therefore, we simply represent the unknown magnitude of the normal force by the symbol lowercase n, written without an arrow on top. Now we break the normal force into components. The normal force is parallel to the y-axis. So we apply this rule. N sub y, let's see here. The normal force points in the positive y direction. So n sub y should be positive, and n sub y should have the same magnitude as the overall normal force, which we're representing by lowercase n, and the other component should be 0. We've applied this rule to break the normal force into components. Now we're ready to work on the frictional force in our force table. We'll use this method. Were we given a value for the magnitude of the frictional force? No, we were not. We were not given a value for the magnitude of the frictional force. So we ask this question: is there a special formula for the magnitude of the kinetic friction? Yes, there is a special formula for the magnitude of kinetic friction. Here's that special formula. F sub k equals mu sub k times little n. First, we write the general formula. Now we start plugging in specifics. What are we going to plug in for mu sub k? Well, the problem didn't give us a number for mu sub k. In fact, remember the question is asking for mu sub k. Well, if we don't know the value of a concept, we just continue to represent it by a symbol. So I'm just going to continue to represent the unknown value of mu sub k by the symbol, mu sub k. And also, we don't have a value for little n, do we? Remember, we don't have a value for little n yet, so I'm going to continue to represent this by little n as well. So this is the general formula. The general formula for the magnitude of kinetic friction is mu sub k times little n. And on this particular problem, the specific formula that we happen to be using happens to use the same symbols. We happen to be continuing to use mu sub k and little n as our specific symbols for these concepts in this problem. So you might think that we haven't made any progress, but remember we saw in the previous video that we don't need to have a number or a symbol in the first row. It's okay to have an algebraic expression. So here we have an algebraic expression for representing the magnitude of the kinetic friction, and we can just put that algebraic expression in the first row of our force table. So I'm just going to copy that algebraic expression here in the first row of the force table. We'll say that the magnitude of the kinetic friction is represented by the algebraic expression mu sub k times little n, because so far we haven't been able to substitute any specific values for either of those symbols. I think this is the first problem where we weren't able to plug in any specific numbers for a special formula. But you can see that you shouldn't let that concern you too much. If you can't plug any specific numbers into your special formula, then you just continue to use symbols in the special formula. That gives you an algebraic expression for the magnitude of the force, and we just write that algebraic expression here in this first row of the force table. Because we turned out not to really make any forward progress with our work over here, I guess I may as well go ahead and erase that work. if it was obvious to you on this problem that you were not going to be able to plug in any specific numbers yet for the special formula, you could just write that special formula directly here in our force table. Now, if all we have is this algebraic expression, is that going to prevent us from breaking this force into components? No, we can still quite easily break this force into components. So let's go through the steps for that. Notice in our free body diagram that we can see that the kinetic friction is pointing anti-parallel to the x-axis. The kinetic friction is pointing opposite to the positive x-axis, and that's a situation where we can apply this rule. Because the force is anti-parallel to the x-axis, that tells us that the x component should have the same direction and magnitude as the overall vector. Well, our overall vector here is pointing in the negative x direction. So we should say here that this kinetic friction is going to be negative. And now the magnitude of the x component should be the same as the magnitude of the overall vector. Well, we are representing the magnitude of the overall vector by the algebraic expression, mu k times little n. So we'll represent the magnitude of the x component by that same algebraic expression, mu k times little n. And then the component for the other axis, the y-axis, should be 0. So we were able to use this rule to break the kinetic friction force into components. And you can see that the fact that we had an algebraic expression for the magnitude of the kinetic friction didn't prevent us from breaking it into components. And the fact that we hadn't been able to substitute any specific numbers into our special formula for kinetic friction, that also did not prevent us from using this algebraic expression to break the kinetic friction into components. This negative sign is crucial. If we leave out this negative sign, we're going to get the problem wrong. Remember that if you put a plus sign in front of all your positive components, you're much more likely to remember the crucial negative signs in front of your negative components. Now, the magnitude of the normal force on this problem will be determined by how the normal force interacts with the weight force. And you can see from this special formula that the magnitude of the kinetic friction will be determined by how the kinetic friction interacts with the normal force. But, as usual, for purposes of filling out this force table, we did not try to figure out or predict what the result of those interactions will be. We're simply going to let this formula and later let the Newton's second law equations figure out the interactions for us. We completed this step. We represented the magnitudes of the overall vectors. And for the frictional force and for the weight force, we used special formulas to represent the magnitudes. And for the normal force, we just represented the magnitude with a symbol. Then we broke the forces into components, including a plus or minus in front of each non-zero component. And we used the value, symbol, or expression for the overall magnitude to represent the components. We used the value, or the symbol, or the algebraic expression for the overall magnitude to represent the components. Now we move on to the Newton's second law equations. First, we write the equations at the top of two adjacent columns, like so. Now this sigma symbol tells us to add. So here we're adding all the individual x components of the forces. W sub x plus n sub x plus f sub kx. And again, this sigma symbol tells us to add. Here we add all the individual y components of the forces. W sub y plus n sub y plus f sub ky. Now we can plug in more specifically for the components from our force table. W sub x is 9.8. N sub x is 0. f sub kx is negative mu k times little n. Negative mu k times little n. W sub y is negative 17. N sub y is n. F sub ky is 0. The sigma symbol means add, but notice that some of the components that we're adding include negative signs. Here we're adding a negative component, and here also we're adding a negative component. For the mass, we should plug in 2 kilograms. Now we plug in for a sub x and a sub y. Well, this object is moving down the ramp. We're moving parallel to and down the ramp. That means that the object is moving only in the x component. There is no motion perpendicular to the ramp. That means that there is no motion in the y component. This object is motionless in the y component. Since the object is motionless in the y component, a sub y is 0. Now, what about for a sub x? Should we plug in 0 for a sub x? Well, clearly not. The object is clearly not motionless in the x component. There's no reason to think that the object is moving with constant velocity in the x component, so there's no reason to plug in 0 for a sub x. So how should we handle a sub x? Should we just keep representing this concept by the symbol a sub x? Well, no. Did you notice or remember that on this problem, the problem told us the value for a sub x? The problem gave us a value for a sub x. The problem said a sub x equals plus 3.0 meters per second squared. So clearly we should substitute this value for a sub x into our Newton's second law equation. We can substitute the value of 3 meters per second squared for a sub x. Just to make the math a little simpler, I'm not going to substitute the plus sign there when I substitute the number into the equation. So did you notice or remember that number? Make sure that you keep reading and rereading the problem throughout your solution to make sure that you are obtaining all the necessary information. By the way, I hope that you have all these problems printed out during the video explanation so you can keep restudying the problem. Remember, there's a problems document that you can use to print out each problem. You should have the problems printed out while you're working on them and also while you're watching the video explanation, because it's crucial to keep rereading and restudying the problem throughout your solution and throughout the process of watching the video solution. Okay, so the problem gave us a value for a sub x, and we substitute that into this equation. Now we can make some simple simplifications. Adding a negative can clearly be rewritten as a subtraction. I guess I might as well do this easy calculation as well. 2 times 3 is 6. We completed this step. We've completed this step, adding the force components including negative signs. We substituted for mass and for a sub x and a sub y, and we used this rule. Since the object was motionless in the y component of the acceleration was 0. Now we're ready to use algebra to solve the Newton's second law equations. Which equation should we work with first? Well, recall that the problem is asking us for mu sub k. So it would be natural to want to start with the x equation, since the x equation is the one that has the symbol mu sub k. But are we ready to work with the x equation? Count the unknowns. There are still 2 unknowns. 2 unknowns, mu sub k and little n, in our x equation, and that usually means that we're not ready yet to work with an equation. How about the y equation? The y equation has only 1 unknown at this point, only little n. So it looks like actually we need to start by solving the y equation for little n. The problem's not asking us for little n, but then we could substitute little n into the x equation and then solve the x equation for mu sub k. So that gives us a plan for solving the problem. To determine which equation you need to work with first, count the unknowns. This equation is easy to solve by adding 17 to both sides. We're adding 17 to get rid of the negative 17. The units for the normal force are newtons. And now we should ask if this result makes sense. Even though this is not what the question was asking us for, anytime you get a result, you should ask if it makes sense. Does the sign of this result make sense? Well, this result came out to be positive. Remember that this symbol, written without an arrow on top, stands for the magnitude of the normal force. So yes, it does make sense that this result came out to be positive, because a magnitude should never be negative. Now let's ask ourselves whether the size of this result makes sense. Well, the purpose of the normal force is to prevent the object from moving through the solid surface of the ramp. And who is trying to start the object moving through the surface of the ramp? It is W sub y. The y component of the weight is the force that's trying to start the object moving into the surface of the ramp. So to keep the object motionless in the y component, so it doesn't start moving through the surface of the ramp, the normal force has to cancel W sub y. Notice this is a version of the free body diagram where the weight force has been broken into components. Well, earlier we discovered that the magnitude of W sub y is 17 newtons. So in order to cancel W sub y, the magnitude of the normal force has to also equal 17 newtons, and that's the result that we got. So we can see that the size of this result makes good sense. It makes good sense that the magnitude of the normal force has to be 17 newtons to cancel W sub y. Notice that I tried to draw this arrow for the normal force the same length as this arrow for W sub y in this new version of the free body diagram to show that the normal force has to cancel W sub y. Well, remember that the problem wasn't asking for the magnitude of the normal force. The problem was asking for mu sub k. So we have to continue with our solution now. Well, now that we've finished with the Newton's second law y equation, the logical thing to do is to substitute this value for little n into the Newton's second law x equation to reduce the number of unknowns. We're making this substitution. For little n, we're going to substitute 17. And now notice there's now only one unknown. There's only one unknown left in the x equation, mu sub k. Now that we're down to only one unknown, we're ready to solve the x equation for mu sub k. First of all, I guess I'll rearrange this multiplication. It doesn't matter what order we multiply mu sub k and 17, so it would be simpler to write the multiplication like this, because that allows us to get rid of the parentheses. Now we have to get mu sub k by itself. First, I'm going to move this term to the right-hand side by subtracting 9.8 from both sides. I'm subtracting 9.8 to get rid of the positive 9.8. Always take your time and be careful when there's negative signs in your algebra, because it's easy to make mistakes with those. We have to do the calculation 6 minus 9.8. So for that, we'll get negative 3.8. Again, be careful with the negative signs with these calculations. Now, to continue to get mu sub k by itself, we have to divide both sides by negative 17. That lets us cancel the negative 17 from the left-hand side, so we're left just with mu sub k on the left-hand side. And now we have to do our calculation, negative 3.8 divided by negative 17. Since this digit is a 5, I guess I'll round this digit up to a 4. So that gives us 0.224. 4 for mu sub k. Normally, when we get a result from an equation, we should put the units in. But do you remember there are no units for the coefficient of friction? The coefficient of friction has no units, so we don't need to write any units here. Notice how we continue to arrange our math in two adjacent columns. I encourage you to imitate this approach in your own scratch work. Organize your math in two adjacent columns, as we've been illustrating in the videos. Now we should check if this result makes sense. Well, does the sign of this result make sense? This result came out to be positive. Does that make sense? Yes, it makes sense because mu k can never be negative. Mu sub k can never be negative. So it makes sense that mu sub k came out to be positive. If we had gotten a negative mu sub k, we would know we had made a mistake. Now, what about the size of this result? Does the number 0.22 make sense as the result for mu sub k? Well, do you recall that on typical problems, mu sub k will almost always be less than 1? This is the typical range for mu sub k that you'll almost always see on problems. So yes, this makes sense because 0.22 is between 0 and 1. If you had gotten a result for mu sub k of, say, 1.2, that would almost certainly be wrong, because on typical problems, mu sub k would almost never be greater than 1. So this would be a result that would almost certainly be wrong. So yes, this result does make sense because it's in our typical range for mu sub k. Let's go back to this friction handout to review some of the key ideas that we were talking about now about coefficients of friction. So we mentioned that mu sub k has no units for mu sub k, and we saw that the typical range for mu sub k is between 0 and 1. We used that to check that our result made sense. This is what the problem was asking us for, so now we're ready to write our answer to the question. Here's our answer. The problem was asking about the coefficient of kinetic friction. The data in the problem seems to be given to 2 digits, so I rounded off this result a bit more to 2 digits. Okay, so now we've completed this step and we can make some checks on our answer. We should check that we answered the right question and that we answered all parts of the question. Well, yes, the question really was asking about the coefficient of kinetic friction, and it wasn't asking about anything else. Make sure you read the question carefully. It was possible that the question could have asked you for the force of the kinetic friction. A different problem might have asked you for the force of kinetic friction, and that would require a different answer. So read the question carefully to make sure that you're actually answering what the question is asking you for. This question was asking for the coefficient of kinetic friction, not for the force of the kinetic friction. We've already checked that our answer makes sense. We already mentioned that the coefficient of friction doesn't have any units, and this check is not relevant for our numeric answer. Looks like we finished the problem, and it's time for a recap. Here's a summary of some of the main steps in our solution of this problem. I believe this problem is only the second problem that we've worked on that involved kinetic friction. So our main goal in this problem was to get more practice with working with kinetic friction. In our free body diagram, we find the direction of the kinetic friction by remembering that friction opposes sliding. And in our force table, we represent the magnitude of the overall kinetic friction with the special formula, mu k times little n. The new issue that came up on this problem that we hadn't seen before is that in this case, we didn't have any specific numbers to plug in to the special formula. But notice that that did not hinder our solution. If you don't have any numbers to plug in for the special formula, then you can simply use that special formula itself as an algebraic expression to represent the magnitude of the overall force. And then we were still able to represent the components using that algebraic expression, mu k times little n. Remember to organize your math in these two adjacent columns. Notice, well, how did we know what order to work on the equations? Remember that we counted the unknowns. Earlier we saw that there were 2 unknowns in the x equation and only 1 unknown in the y equation. That told us to start by solving the y equation for little n, and then we substituted that value into the x equation so that we were able to solve the x equation for mu sub k. To determine the order that you're going to work with the Newton's second law equations, count the unknowns in the equations. Again, I'll remind you how important it was to include the key negative signs on some of our negative components. So make sure you're putting plus signs on your positive components to help you remember the negative signs on your negative components. Okay, well, I hope that now you feel that you've developed a good foundation in the skills for working with kinetic friction. And hopefully those skills will serve you well as you continue to work on more difficult problems, beginning with the next problem in this video series. Did you find this video to be helpful? If so, you can support the videos by making a monthly pledge of $1 or more at my Patreon page. You can visit my Patreon page by clicking the link on the screen or by using the link in the video description box. Thank you.